Hello, everyone. I hope we just had a nice little journey with Ted, going through many years of experience as we went through all of this, and also geologic history throughout New England. What I'd like to do is to essentially take it to the next level and look at wells themselves and talk a little bit about them and why they're so important, the things that we do to them as part of this process. So we'll start out by looking at sort of the types of common water well designs, and we'll just skip over this quickly. Water well terminology, which hopefully a lot of people are familiar with, and a term that you're going to walk away with called specific capacity, that if you leave this webinar and don't remember what specific capacity is, then we haven't done our job. Groundwater and well terms, which should be familiar with many people. One really important thing, which we touched upon, Ted touched upon a little bit, is groundwater flow into the well screen. Why it's important, why we need to know what it is. A term which people don't think too much about unless you're actually designing wells, but when you operate them, you don't really think about it very much, but the entrance velocity of that particle of water that's entering that well screen. And all of the things that I want to talk about sort of follow the AWWA, American Water Works Association, A100-06 standard. So we try to keep this so that everyone can follow this no matter where you are in the US or around the world. So why is all of this important? You know, what's this all about? And the two little pictures that you have on the screen, the top one is before, and even though it looks like sort of an orangey brown, sort of reddish orange brown, I can't see very much there. Well, that's because that's when the well screen, if you're a sand and gravel well in most cases, becomes clogged and fouled or biofouled with iron bacteria, such that the transmitting capacity of that well screen is minimized, which has an important role on our little term that we're going to learn, a specific capacity. Our goal when we're doing a well redevelopment is what we see at the bottom picture here. It's the after picture, and now we can actually see the internal structure. We're inside the well now, and we can see the vertical rods in there. We can see the trapezoidal wire wrapping around it, and we can see the openings between the trapezoidal, which is the screen slot size, but also we can sometimes see the gravel pack or the natural formation on the outside. So we've gone from something where we don't know really what it is in the top photo to the bottom photo is BAMO. This is what we're trying to do, cleaning up the well so that we can get the water coming into the well screen and we have a really efficient well. Well, the design of a water well is not cookie cutter. It's not, we'll do it here like we did it everywhere else. Each one is unique. Just as like each person is unique, each well is unique. And some of the key factors that go into developing a well and where to put the well, and Ted alluded to some of this stuff in his presentation, is the location of the well. Where are we going to put this? You know, what's the formation like? Is it coarse grain material? Is it finer grain? What's the transmissivity of that material? You know, what well materials are we going to use to build it? Are we going to use a shutter screen? Are we going to use a trapezoidal Johnson type well screen? Or are we just going to cut a bunch of holes in some PVC and use that? Proper installation. You want to make sure that the people installing this well have done it before. They know what they're doing. The people that you have working for you as consultants or engineers or hydrogeologists have done this before and they know what to do. One thing that sometimes gets left off is the development of the well. When the well has been installed, everything is ready to go. We want to make sure that we remove as many of the fine materials around the well screen from the formation as we can in order to make the well as efficient as we possibly can given the design. Now, what we're trying to achieve here is efficient and dependable well with a long service life, like 75 years or so. This is what we're trying to get out of this, because wells are expensive to put in, land is expensive to purchase, so we want to make sure that we do it right at the beginning because it's going to be there for a long time. Some basic water well terms most people are familiar with. We have our ground surface at the top, our pump, our observation wells that Ted spoke about a little while ago usually 2 foot off center from the well that we want to install. We have our static water table. Remember back from our introductory hydro courses or basic geology courses that the static water level is a dynamic feature. It does not stay in one spot throughout the year. It moves up and down depending upon the amount of recharge we get in the springtime, and as we go through the growing season, water table begins to drop naturally because of seasonal demands by vegetation or by everyone. So locally around here, to see a 3 to 10 foot drop in the static water level over the growing season, over the summer, is not unusual. So we do see that. As we stress the well, in other words, we start to pump it, we see the water table, the static water table gets depressed, form a little dimple in it. That new water level that we're measuring is called the pumping level. So that's the pumping level that we get in the well. The static water level to the pumping level, that's the drawdown as a result of pumping. Terms that are fairly straightforward. The term that's really important is the one off to the right. It says available drawdown. The available drawdown is where your static water level is, say in your maximum, your stream, your springtime water level, to where you have an elevation, say about 5 feet above the top of your well screen. That's a little safety factor. That's your available drawdown. Your available drawdown changes throughout the course of the year. It drops because of natural conditions. So you have to take this in consideration when you're developing the well and trying to understand what the yield of your well is going to be. Now we have a couple terms, little equations down below, which are just written out. Specific capacity, specific capacity. This is something we'll remember when we walk away here. Hopefully we won't have any bad dreams over this after we see it so many times. But specific capacity is nothing more than the pumping rate, whether it's gallons per minute, liters per minute, whatever that number is, it is the pumping rate, or Q, divided by the drawdown. So take the pumping level, the static water level, subtract the two, that's the number. It gives you a number which is dimensionless, so pumping rate over drawdown. So our goal when we put in a well is to maximize that specific capacity. We want to have the highest number as possible, the greatest amount of pumping rate with the smallest amount of drawdown. Now we can make an estimate of what we think the yield is going to be, and Ted talked about this a little while ago. If we know what the specific capacity is times the available drawdown. Now we know the available drawdown is a number that is not a fixed number, but it'll give us an idea of what we think the yield of the potential yield of that well is. So some simple little terms just to keep everyone familiar and everyone on the same wavelength here as we go through. Probably one of two equations that we're going to see. We're just defining what specific capacity is, even though we just talked about it. And we're looking at it, and we just give a little example on the bottom with Q equals, we just said 100 gallons a minute divided by 10 feet of drawdown. So our Q, or our specific capacity actually, is 10 gallons per minute per foot. So that's the number we're looking at, specific capacity, 10 gallons per minute per foot. That's really important. So anytime we come back to redevelop our well, we want to, that's our baseline number that we want to come back to. We'll talk about that more as we go on. We have a couple of examples here. In this case, it's a large capacity sand and gravel well. We're measuring the specific capacity versus time, specific capacity on the y-axis, time on the x-axis, from, in this case, 1966 through 2011. If we see the green line at the top, horizontal line, it says new construction. That was our specific capacity back then. Okay, we draw a red dashed line, which is the 15% decrease in specific capacity. That's sort of a magic little number that we use. Other people may have something a little bit different, 15 or 20% drop off in the original specific capacity. At that point, you're saying, wait a minute, I'm having to pump this well harder to get the same amount of water, which means I'm also costing me more money in power in order to get that same amount of water. So I need to do something. So if you're constantly measuring this, and we'll talk about how we do that, then you'll know when you reach this 15% loss, 15, 20% loss. If you don't do that and you come back sometime in the future and say, oh, wow, my specific capacity is no longer like 45, but now it's something about 25, my well is having a real problem. So let's redevelop it. So when it was redeveloped, we were able to get the specific capacity, if you go to the far right here, back up to around 40, which still wasn't back to where it was when it was really installed. And this does happen where you've let it go so long without redeveloping it. And then at some point you said, okay, I have to watch this a bit more. So it was only a year or two later when you redeveloped it again, and now you're able to bring it back up. And in some cases, you can get it up a little bit higher to when the new construction was put in, because you're cleaning out more of the surrounding aquifer around the well screen in order to get more of the fines out to improve the efficiency of the well. And we just showed, again, as it declines with time, but it's being monitored now so that they know when to redevelop the well. Really important to do this, really important to set up a program. And you want to make sure that you measure your specific capacity at the same time of year, each year, because you have different water levels and maybe different water chemistry. So you want to compare apples to apples and not apples to orange when you do this. Here's a large capacity bedrock well, and this again, a little shorter time period, but notice the specific capacity of the bedrock well is only 1.5 as opposed to 10, which we just saw in the sand and gravel well. We find for virtually all bedrock wells, the specific capacity is really low. If you have it around 1 or so, that's a really great bedrock well. This one is about 1.5. And we notice the specific capacity lasts a lot longer than in the sand and gravel well. Well, it's because water, as we know, travels through the fractures in the bedrock as opposed to the small interstitial spaces in the sands and gravel deposits. So specific capacity lasts a little longer. In this case, as with the pumping, it actually opened up the fractures a little bit more. And then when the well was redeveloped, after a number of years, it came back up. We'll see in later webinars that the type of redevelopment is a little bit different in sand and gravel wells than we have in bedrock wells. So our job when we put in wells, anytime we install them, is to maximize the development of the well screen during construction, because in the future, we want to have our baseline, we want to redevelop that well so it can be returned to the original specific capacity of that well or better. And then we know we've done a good job both in the installation of the well, but also in our redevelopment. Any questions as we move forward here?
Hi, Ray. We do have one question, and that's about tracking specific capacity at the same time every year. Do you know if there are certain devices that are good for doing that automated tracking?
Yeah, years ago, most people never monitored anything, but now most people have recording pressure transducers in their wells. Most times, especially for public water supplies, they're typically hooked up to their SCADA system, their automatic SCADA system, and the data is collected literally every day. And there's an algorithm that's typically put together in the software package for SCADA that actually does the calculation and actually will do the graphing of the specific capacity for you. So it's really important to do this, and you can track it all the time, and it's a useful tool for all operators or anyone operating a system, because you'll understand how the well is operating and to know when it's time to put a budget in to begin to redevelop your well. Good question.
Thanks. And that's all we have for now. So back to you.
Okay, great. So some types of common groundwater supplies, Ted talked a little bit about them. We looked at the open borehole, which is simply a bedrock well, naturally developed ones, and those can be, or gravel packed ones, which can be single gravel pack or multiple gravel pack. We typically look more at the single gravel pack these days as opposed to something multiple ones. These little cartoon little diagrams, the first on sand and gravel deposits and sort of stratified drift, which Ted was talking about, which is the material we want to look into because that will give us our best aquifer transmissivity, will give us the higher volumes of water. And the little diagram on the left is kind of interesting because we have our well screen inside, and then on either side of it we have our gravel pack or a natural one. But note that the pictures that we draw, which is really nice, pretty gravel packs or naturally developed on either side of the well screen, doesn't always occur that way. But sometimes we'll get areas where we see the coarser material migrating away from the well screen, as we see in the little diagram on the left. And what does that do? That provides better pathways of water flowing into the well screen. So even though we think that the uniform well openings on the well screen are there, we may find that the water flowing into that well screen goes along preferential pathways into that well screen and not uniformly everywhere the same way into that well screen. Kind of interesting. The little picture on the right is we see fractures and we see a major fault zone, and actually that's Ted standing down there, that little person standing down there, but we can see the offset quite clearly in the diabase dike that's being offset along that fracture zone. This little diagram, we've seen it once before. It's the types of common water supply. Remember, in fractured rock systems, the flow of groundwater is along fractures, which can be primary cooling fractures depending upon the rock type, or secondary or structural or tectonic features, more largely what we see around sort of in the New England area, as opposed to primary cooling ones or along sedimentary ones in sediments or in conglomerates or in limestone type features. This diagram here was taken directly out of the AWWA manual, and we can show lots of different types, but the one on the right, which is figure J.2 type 2, and I draw it only to show you in the bottom right hand where the little circle is around it, because we want to focus in on that area, which is right around the well screen itself. As we see in the little diagram on the left, it's actually, this is a diagram of naturally gravel developed wells, but the picture on the right is actually the well screen is to your left. The trapezoidal wires for the well screen are there, and then as we go to the right, we get into the gravel pack, which is essentially a uniform material that's separating from the formation itself. We do this when it's a little bit difficult to remove the fines from the formation so that we cannot get evenly distributed or a really uniform type of material against the well screen. So we're looking at a gravel pack on the one on the left. On the one on the right, a little bit different. We actually have the well screen, and then we're able to draw out a lot of the finer grain material such that we're developing a natural gravel pack around the well screen after we've pulled out a lot of the fine material. So both of them operate the same way. One is the formation where we're actually pulling the fines out, and the one on the left is the actual where we put a gravel pack in. So groundwater flow into the well screen, what do we want to do? You know, what do we want to minimize? Because this is a turbulent environment. We may not think it is. We think groundwater moves slow, but it does. But as soon as you put a well in there and you start to stress the aquifer and withdraw water, things really happen very, very differently. But what we want to do is we want to minimize that turbulence around the well screen. We want to be as uniform flow going into that well screen as possible. We want to reduce those large pressure changes going from the formation into this well screen. We want to minimize the precipitation of iron, manganese, and calcium deposits, which are going to occur on these small slot sizes as it goes into that well screen. A key thing here too is we want to minimize the entrance of particulates, fine grained material into the well screen. Why is that important? Well, because it'll get sucked up into the pump or the pump mechanism, and now we'll begin to abrade it, pretty much like sandpaper does to wood. And also we want to minimize that release of gases which are dissolved in groundwater, stop these little mini explosions which occur in there, which also change the water quality and may cause the precipitation of calcium carbonate deposits within the well screen. So a lot of things that we have to take into consideration when we do this. So we have two examples, one on the left, one on the right, a slotted pipe, which it can also be the same as a shutter screen, but it's a slotted pipe. And on the right is a continuous slot screen, which is the type of screen that we use now. And what's important here is to look at the arrows, the flow paths going into the openings in the screen itself. For the one on the left, we see that it's not very uniform. We get particles of water banging into each other, all trying to get into that little slot in that screen, in that pipe. And they're fighting with each other, creating more turbulence and more anxiety as the little particles go in there. Whereas the ones on the right, a little bit more harmonious. They try to flow in there. They're radially flowing into that well screen. They're working with each other a bit more nicely and creating a better environment, minimizing a lot of the problems which can occur around that well screen. If we sit up on our helicopter and we look down into the well screen from above, the one on the left is like our slotted pipe, and we can see how the flow lines with the particles of water are converging and smashing into each other and creating a really turbulent and violent environment, more than really we want it to be. Whereas on the one on the right, we see the lines of equal head. We see each particles coming in there. They're kind of like enjoying each other's company as they flow into the well screen. It just makes life a lot easier and minimizing a lot of the problems going into that well screen. What we also want to look at here is that groundwater flow. This is like entrance velocity taken from the AWWA manual. And it's nothing more than the velocity at which the water passes through the well screen. It's a function of three principal parameters. The first is the well screen diameter and length, the slot size, and the pumping rate. The entrance velocity we can be modified by, we can increase the length of the screen, we can do the diameter, we can do a lot of different things to change it, but we still have to figure out what's that velocity, what do we want it to pass into that screen at. And AWWA has, AWWA has a little formula they use, entrance velocity, well yield Q divided by the total area of screen openings. And the entrance velocity that we want to get, and it may not seem like a lot, is 0.1 to 1.5 feet per second. It's not very much, but it's enough. And that's what we want to keep it. Too fast, we have problems. Too slow, and we have problems. Why is it important that we have that sort of velocity going into the well screen? It's important because we want to minimize the well losses. We want to maximize that specific capacity, that SC number. We just need to do that because we want as efficient as possible well. The little diagram we see in front of us is the red line would be the ideal aquifer curve if we had no well losses due to the inefficiencies going into the well screen, the diameter, the types of material around it, the gravel pack or the formation itself. In actuality, we have a cone of depression and we have our actual drawdown, including well losses, which is much greater. 80% or so is what we try to strive for efficiency. And when it starts to drop off more than that, then we have problems. So this is what we aim for. Our goal is this when we install a well, and why we do things the way we do it. So in summary, we've looked at the types of well design and construction. Ted spoke a little bit about this. I went over this pretty quickly. Groundwater flow into the well screen, which is really critical, really important, and why you need to have people who know what they're doing in order to do these calculations. Also, the entrance velocity is important. We don't want it to be too fast or too slow because we want to minimize all the disturbances, maximize the efficiency of the well. And finally, the specific capacity of the well is why we're doing a lot of this, because that's our measure for what's happening to that well and how we can keep it the best way that we want it. We do routine maintenance of our car. We do routine maintenance by going to the dentist, our checkup to make sure that we're healthy. This is the same thing we're doing for our wells. It's specific capacity is kind of the window into how is my well doing? Do I need to address anything that's going on with it right now? So as we move forward here, this webinar is sort of an introduction on how to locate test wells and why it's necessary to maintain their health. Our goal is to keep these wells in service for 75 plus years. This is a huge investment, and we have to teach people, because we'll be looking at 2 or 3 or 4 potentially generations of people who are operating these wells, and we want to make sure that they have all the information they need to keep it healthy as we move forward. So in the rest of this webinar series, this is just an introduction, we'll look at how and why wells lose their efficiency. Why do they clog up? Why do these well screens have problems? The methods to redevelop them, both sand and gravel and bedrock. And we'll look at several case studies that explore the costs associated with the redevelopments. We encourage you to participate in the rest of the series and look forward to seeing you at the next webinar. We thank you for taking your time out of your busy day to spend this time with us and listen to us as we give you some of our experiences that we've developed over many decades of doing this work. Thanks again.